All right, for this problem, we didn't fully get to talk about the concepts needed. We got a preview for it on Tuesday, but we didn't talk about it in detail. So I'll remind you all that we said that for conservative forces, the following is true. You can calculate the conservative force by taking the derivative of the potential energy function that is associated with that conservative force. So two examples of this that we saw were spring force and gravity. So we know for springs, the potential energy function for a spring is 1/2 kx squared. Well, to find the force that you experience from a spring, you would just do minus the derivative of u, and then the variable that we take the derivative with respect to is whatever parameter the potential energy depends on. Here, the parameter it depends on is the compression or extension. So we're going to take the derivative of the potential energy function with respect to x. Well, we get minus 1/2 k, and then the derivative of x squared is 2x. So all of that simplifies to minus kx. Well, this is essentially Hooke's law. The spring force is negative kx for any spring. That works out really nicely and basically demonstrates this idea for springs. Now let's talk about it in terms of gravity. We know that the potential energy function for the gravitational potential energy function is mgy. Well, if we wanted to find force of gravity, technically we should just be able to do minus du, and then the parameter that gravity depends on is the height off the ground, our y value. So we take the derivative with respect to y. Well, the derivative of this expression with respect to y is just mg because it's the constant, and derivative of y is 1, so I get negative mg. And this is, sure enough, the force of gravity, basically acting downward with a magnitude of mg. So this is just to help demonstrate this idea to you. We didn't quite get to it in class. Now, knowing this, let's look at this problem. We're given a particle that's constrained in one-dimensional and is acted upon by a force that's given to us here. Find the potential energy function that is associated with this force, and if u is arbitrarily defined to be 0 at x equals 2, what is our potential energy function going to be? So here's some hints to you for this problem. If you can find force by taking the negative derivative of the potential energy function, well, then you can find the potential energy function by taking the negative integral of force with respect to whatever parameter. So for part A, what you want to do is find u by integrating your force function with respect to x. So taking the integral x cubed dx, and this is going to give you a constant of integration. You're going to get a plus c. You find that constant of integration by plugging in this condition. Basically that when x is equal to 2, your potential energy should be 0, and that'll give you your plus c term. And then for part B, they ask us which direction will it start moving if the particle is let go at 5 meters. Well, ask and see which way is your force pointing when you're at 5 meters. And also, we're starting from rest, so there's no initial kick to the left and right. The movement of the object is going to depend on what kind of force it feels at that location. And then part C and D kind of walk you through the problem, so I'd like you to try these on your own.